Now, back when we discussed forces, we said that what? We had equilibrium, and we defined the fact that equilibrium was when the net force was equal to 0. So we said that the sum of the forces equal to 0 is what defined equilibrium. So it just means that the system is either static, something like this, or at least moving with constant speed, so that there's no acceleration, and this is what we call the equilibrium. Now, the problem with this is that it's not enough. And to give you an example of where it's not enough, let's consider a car. So let's say here's my car. So what do we know? So we know the car has a mass to it, so we know it has a gravitational force pulling down. So it's going to have some mg, which is acting at the center of mass. Now, it could be, based off the distribution of the car, since the engine's in the front, there's typically not as much in the trunk and things like that, that the center of mass won't be at its geometric center, but it's going to be off-shifted, say, to the front, possibly to the back, depending on how the car is situated. But what we also know is that there's normal forces. So this thing has a normal force in this direction, let's call that N2. Also a normal force in this direction, let's call that N1. And here I'm going to assume that if I was looking down the front of the car, that at least the front of the car, the center of mass is along the center axis of the car. So even though there are 2 front wheels and there are 2 rear wheels, I'm going to assume that the normal force on each wheel is the same. Okay, just to make it a little bit easier. So in this case, I actually have 2 unknowns. Right, so I have N1 and N2. So if I was simply looking at the sum of the forces, or if I call this my positive y direction, we would say the sum of the forces in the y direction is equal to 0. So I get N1 plus N2 minus Mg would be equal to 0, which is not enough to solve for both normal forces. The only way I can do this is if these 2 normal forces were the same. In that case, I can solve for 1 normal force. But in most situations, this is not going to be true. So, simply saying that equilibrium based off the sum of the forces is equal to 0 is no longer enough. This is not going to give us enough information to be able to solve this problem. So in a situation like this, where I have 2 unknowns, I need at least 1 more expression, where that 1 more expression has to come from someplace else. And that someplace else is now our new friend, torque. So it also has to be true is when I'm in a equilibrium system, this thing is not going to rotate in this direction or in this direction, which means that the net torque acting on the system must simultaneously be equal to 0. So, equilibrium then is not defined on the fact that the force is equal to 0, but it's defined on the fact that both the force and the torque must simultaneously be equal to 0. So, this gives us now 1 more piece of the equation to be able to determine what equilibrium is. So in a typical sense, if I was working in a 2-dimensional problem, we're going to have, say, 3 unknowns to be able to determine at one given time. So let's do an example. Let's see what a particular statics type of problem is going to look like. So let's say we have something that looks like this. Let me draw you a picture. So let's say I have a wall. So here's my wall. And fastened to this wall, we're going to put a beam. So across here is a beam. So I'm going to buckle this thing down here. And then from the end of the beam, I'm going to put a rope. So that rope's going to point in this direction, which makes this at some angle of theta. And then some distance away from here, I'm going to put a box where this box has a mass of m. And the beam itself also has a mass. Let's call that mass m sub b. And the beam has a length to it. Let's call that length L. And let's put in some numbers. So let's say that the beam has a length of 3 meters, and it has a weight, so it's actually m times g, which is equal to 200 newtons. And what I want to do is put a wood block on here, which also has a weight, so that's m times g, which is equal to 300 newtons. And finally, this angle here is equal to 30 degrees. So this is going to be a slightly different problem than we're going to usually have in homework and things, but basically the idea is going to be the same. What we want to know in this case then is what is the maximum distance x here that we can put our block if the maximum tension in this cord can withstand a maximum amount of, say, 500 newtons. So what I want to know is how far to the right can I move this thing before this string or this cord or this cable breaks. If this thing can withstand a maximum amount of 500 newtons. Now the other thing I want to know is what is the force then on this hinge here? So I want to know what is the vertical amount of force, so let's call that Fy, and what is the horizontal amount of force, Fx. So what I want to know is what is x, also what is Fy, and what is Fx. So what are the maximum values of things that I can have on here? So, now to analyze problems such as this, typically what we're going to look at is where all the load is being put onto it, so where all the forces are acting on, which means we're only going to consider the beam itself. So let's draw the beam. So here's my beam. Okay, there's my beam. And then from here we're going to consider all the forces which are acting on the beam. So the first force we have are these vertical forces. So, or the hinge forces. Now I'm going to assume that the hinge is directly at the end here. So I'm going to say this has an Fy in this direction, this has an Fx in this direction. We'll talk about why we put them in that direction. This also has the mass of the beam itself. So let's call that the weight of the beam. We also have this block that's on here. So that's going to be here, pushing straight down. So this is now going to be the weight of the box. I'm just going to call that W. And we also have the tension, where the tension is going to pull off in this direction. So this is then the tension. Now, first thing we should do is apply Newton's second law. So let's go ahead and call this our y direction, this our x direction, and let's apply all of our Newton's second law for these cases. Now, again, this is a static equilibrium case, so we know that this system has to have zero force onto it. So let's look at the x direction first. So in the x direction, we would say that some of the forces acting in the x direction are equal to 0. In this case, the only two forces are the horizontal force in the hinge, call that Fx, minus then the tension force, or the cosine portion of that tension force, since that thing is pointing in the negative x direction. In the y direction, we would then have all the forces in the y direction, so we have Fy, which is the vertical force on the hinge, minus the weight of the block, minus the weight of the beam itself, plus the sine portion of the tension are all then equal to 0. Now, typically, the way that these problems are going to work, like I said, this one's slightly different than what we're usually going to see, but typically the forces we're going to be looking for are going to be the vertical force on the hinge, the horizontal force on the hinge, and typically the tension. In this case, where I'm going to give you the distance of x here. Now, in this case, the only difference is now I'm giving you the tension and I'm asking you what this x is. So it's slightly different on how I want to solve it, but pretty much the process is still the same. Now, lastly, we then have to do the sum of the torques. So let's look at the sum of the torques. Let's do that. So finally, for the torque, we're going to take the sum of the torques about some pivot point, and that has to be equal to 0. Now, since this thing is a static situation, what that means is there is no natural pivot point. So if I was looking at a situation like this, there is no natural pivot point because this thing isn't pivoting about some particular point. So I'm not pivoting here, or at the center of mass, or here, or any place else. This thing has no natural pivot point. So the way we usually choose how we're going to do the sum of the torques about is we're going to choose a pivot point on here which gets rid of as many unknown forces as possible. And here, what that means is we're going to choose our pivot point to be exactly here. So let's call that point O. And the reason for that is because I'm taking the sum of the torques about the hinge, about point O here, then the distance from the hinge to the vertical force on the hinge is 0, which means there is no torque. The distance between the pivot point, or the hinge, and the horizontal force on the hinge is also 0, which means there also is no torque. Which means that these two forces generate no torque. All the torque is only going to come from all the other forces. So, by doing that, I get rid of two torques that I don't know, which is going to make our expression solve much, much easier. So here we're going to take some of the torques about that point O. Now, when it comes to this, typically what I do is I start off at the pivot point itself, slowly move outward away from the pivot point, and then start simply writing down all the torques. So first, if I start here at the pivot point, I move out. First one I'm going to run into is this guy, which is acting some distance x away from him. Pushing down, which means he's going to rotate in the clockwise direction. So since he's rotating in a clockwise direction, this would then be a negative torque. So I get a minus the distance, which is x. Right? So again, this distance from here to here, which is what I'm looking for, is x, times the force, which in this case is simply the weight, times sine of the angle, but again, here my r vector points from here to where the force is acting, times this guy, so the angle between the two is simply 90 degrees, sine of 90 is simply equal to 0. Great. Keep going out. Next one I run into is the center of mass weight. Here, that's going to cause it to move in this direction, again with a negative torque. So I get a negative times the distance from here to here, where this has a total length of L. This is at the center. So it's going to be L divided by 2, times the force, which in this case is the weight of the beam. Again, my r vector is going to point along the straight line here. Again, this is going to be a 90-degree angle. So this is the sine of 90, which is simply 1. Finally, the last thing I run into is the tension out here. Tension is pulling in this direction, so there's a counterclockwise rotation. So it's going to be a positive torque, times the distance, which in this case is the entire length of the rod. But here we have to be a little more careful. So what's happening here then is now my r vector points this way. This is my r vector. My tension points this way, so this is actually the angle between those two vectors. Good. So now, when I write this out, I actually then want to take sine of this entire angle, angle phi. But angle phi is the same thing as what? Pi minus theta. So it's actually going to be the same thing then as L times the force, which is then going to be the tension, times sine of the angle, which is 180 minus that angle of theta, which in this case is 30 degrees, times the, which is all equal to 0. Now, one thing to point out, the sine of 180 minus that guy is actually the same thing as sine of that angle. So if I rewrote this, what I get in this case then is that minus x times the weight, minus L over 2 times the weight of the beam, plus L times the tension times sine of that angle is equal to 0. Good. So again, in a typical situation, you'd be looking for the unknown forces. The unknown forces would typically be the tension and then the vertical and horizontal components. So basically from the torque, you would find the tension. Once you know that tension, you would plug that into here to find the vertical component, plug it into here to find the horizontal component. In our case, a little bit different because what we're told is we're looking for the maximum distance we can move for the maximum amount of tension, which means that here we're going to use the maximum tension to find that distance of x. Here, since we know the maximum tension, we know these, we can easily solve then for fx and fy. So those are easy substitutions in this case. So in our case, what we care about is the maximum tension, the maximum tension, the maximum distance of x, and the maximum tension. So good. So from here, fx is simply then equal to the maximum tension times cosine of the angle. So plug in my numbers. What I find in this case then is that the horizontal force is going to be 433.013 newtons. From here, we get the vertical portion is then equal to the weight of the block plus the weight of the beam minus the maximum tension times sine of that angle. Plug my numbers, what I get in this case is 250 newtons. And then finally from here, we can then solve for the x. So I would simply add that term over here and then divide everything by the weight. So finally I would get x max is then equal to L. Let's factor that out. So I get an L times T max sine of the angle minus 1/2 of the weight of the beam, all divided by the weight of the block. Plug in my numbers, what I get in this case then is this works out to be 1.5 meters. This is the maximum distance I can move. Now, let's go back to here. So why did I draw this guy this way and this guy this way? Well, so let's think about what's happening here. So if the only thing that's really supporting this is the tension on the string here, what does the side of the beam want to do? Well, due to the gravitational force pulling down here, this thing is going to want to do that, right? So this end wants to drop down, which means that the vertical portion on the hinge must be pulling up to make sure this thing doesn't drop down. Simultaneously, as this thing drops down, this tension pulling in this direction wants to pull this guy into this direction. So as it falls, it's going to do this, which means that the tension pulling in this direction naturally wants to push it through the wall, which means the wall has to push back, i.e. the hinge has to push back in this direction to make sure that it's flat horizontal. So this is equilibrium. So again, equilibrium, also known as statics, you simply have the sum of your existence is equal to 0. So the sum of the forces and the sum of the torques must all be equal to 0 all simultaneously. Depending on how many dimensions that you're working in, this will give you the number of components that you have that are unknown. So if I'm working in 2 dimensions, such as this, I can have up to 3 unknowns. So the vertical portion and the horizontal portion on the hinge, as well as the tension in the string, or something else, like in this case, vertical, horizontal, as well as that distance of x. If I'm working in 3 dimensions, that means I have 4 unknowns. Because I have 3 now, sum of the forces, so in the x direction, the y direction, and the z direction, as well as the sum of the torques, which will give me 4 equations with 4 unknowns. So in that case, it would just depend on what it is that you're asked to know. As far as this class is concerned, it would always just be 2 dimensions, so you'd have 3 unknowns with 3 equations. But this is statics. So for you engineering types, you're going to have an entire semester based off of this. Aren't you lucky?